There is a place at the centre of our galaxy where the laws of physics as you experience them every day cease to be useful guides to survival. Not broken, not repealed, still operating perfectly with the same mathematical precision they operate everywhere else in the universe. But operating in combinations, at intensities, and across spatial scales so far outside the range of anything that shaped human biology that the distinction between broken and operational stops mattering. The galactic centre is 26,000 light-years away from where you're sitting right now. It is separated from you by so much empty space that the light currently leaving it will not arrive at Earth for another 26,000 years. It is, in every practical sense, unreachably distant, a place so far beyond the frontier of human exploration that no serious crewed mission planning document has ever listed it as a target. And yet astronomers observe it constantly. They have mapped it with radio telescopes and X-ray satellites and infrared observatories for decades. They have watched stars in its vicinity moving at velocities that dwarf anything in the rest of the galaxy. They have detected X-ray flares erupting from its centre with energies that make our sun's most violent outbursts look like a struck match held next to a thermonuclear blast. They have measured magnetic fields thousands of times stronger than anything in our galactic neighbourhood. They have confirmed the presence, at the precise geometric centre of the Milky Way, of a black hole 4 million times the mass of our Sun, a gravitational monster so dense that the escape velocity at its event horizon is the speed of light. What they have built, through decades of observation across every wavelength of the electromagnetic spectrum, is the most complete portrait available of an environment that is not simply hostile to human life. It is hostile to matter itself. Not all matter, not universally. Stars burn there, gas clouds exist there. A dense population of stars orbits the central black hole in configurations that have no parallel anywhere else in the galaxy. Matter persists. Matter even, in some sense, thrives. The galactic centre is one of the most energetically active environments in the Milky Way. But human biology, the specific, fragile, extraordinarily Earth-adapted arrangement of chemistry and electricity that constitutes a living person, would not persist. It would be taken apart. Not at once, not with the drama of a Hollywood disaster sequence, methodically, layer by layer, by radiation that penetrates any shield a spacecraft can carry, by magnetic fields that disrupt the electrochemical machinery of every cell, by gravitational tidal forces that operate on timescales and at intensities calibrated not for the survival of anything small and biological, but for the shaping of stars and the grinding of gas clouds into accretion disks. This is the story of why. Not a story about the impossibility of getting there. That is a separate problem, addressed elsewhere. This is the story of what is actually there, what the physics of the galactic centre actually does, what the specific mechanisms are by which the environment at the heart of our galaxy would end any human mission that arrived within its influence, and why understanding those mechanisms changes how you think about where we are, 26,000 light-years from the centre, in a quiet suburban arm of an ordinary spiral galaxy, and why that address, which sounds unremarkable, is one of the most important facts about the conditions that allowed us to exist. But before we begin, if space fascinates you, a like and subscribe means everything to us. Let's begin. Before you can understand why the galactic centre is a death trap, you need to understand the structure of the galaxy you're inside, because the Milky Way is not uniform. It is not a homogeneous disk of stars distributed evenly from edge to centre. It is a system of dramatically different environments, each with its own characteristic density, radiation level, stellar population, magnetic field strength, and degree of astrophysical violence. Where you are matters enormously, and where you are is as far from the most dangerous part of the galaxy as a terrestrial address could be. The Milky Way is a barred spiral galaxy, a flattened disk of gas, dust, and approximately 200 to 400 billion stars, roughly 100,000 light-years in diameter and about 1,000 light-years thick at the disk. Across its face, spiral arms of denser stellar and gas concentrations wind outward from a central bar-shaped structure of older stars. Our solar system sits in one of these spiral arms, the Orion arm, a minor spur of the larger Sagittarius arm, at a distance of approximately 26,000 light-years from the galactic centre. This address places us in what astrobiologists call the galactic habitable zone, the range of galactic radii where conditions are favourable for the emergence and persistence of complex life. Not too close to the galactic centre, where radiation densities are lethal and supernova rates are catastrophically high. Not too far out in the galactic disk, where the metallicity, the abundance of heavy elements necessary for rocky planet formation and complex chemistry, drops too low to support the construction of Earth-like worlds. The galactic habitable zone is an annular region spanning roughly 13,000 to 33,000 light-years from the centre. Our solar system, at 26,000 light-years, sits comfortably within it. This positioning is not coincidental from an evolutionary perspective. The conditions in our galactic neighbourhood are precisely what permitted the formation of a rocky, iron-cored, magnetically shielded planet with enough heavy element abundance for complex chemistry, orbiting a stable middle-aged star in a region quiet enough for that stability to persist for the 4 billion years required for biological complexity to emerge. Move inward from our position toward the galactic centre, and every one of those favourable conditions begins to degrade. The stellar density increases, the supernova rate increases, the radiation environment intensifies, the interstellar magnetic fields strengthen, the gravitational dynamics become increasingly violent as the mass of the central region dominates the orbital mechanics of everything around it. By the time you reach the inner few thousand light-years, the region astronomers call the central molecular zone, you are in an environment that bears no resemblance to the galactic neighbourhood where life evolved on Earth. And by the time you reach the innermost parsec surrounding the central black hole, the region called the central parsec, spanning roughly 3.26 light-years around the galactic centre, you're in one of the most extreme astrophysical environments in the observable universe. The journey from Earth to the galactic centre is not a journey across empty space with a dangerous destination at the end. It is a journey through a gradient of increasing hostility, a progressive intensification of every environmental threat that makes deep space dangerous at all, culminating in a region where the threats compound each other in ways that create a survival environment qualitatively different from anything in our cosmic neighbourhood. Understanding that gradient requires understanding each threat in detail, beginning with the one that begins killing you before you are anywhere near the centre. The galactic centre is a source of radiation across virtually the entire electromagnetic spectrum, and the intensity of that radiation at various wavelengths constitutes the first and most persistent threat to any mission attempting to approach it. In the radio band, the galactic centre glows with synchrotron radiation, electromagnetic emission produced by charged particles spiralling through intense magnetic fields. The radio emission from the galactic centre is so powerful that it dominates the radio sky in the direction of Sagittarius, the constellation toward which the galactic centre lies from Earth's perspective. In the infrared band, the galactic centre blazes with thermal emission from dense concentrations of warm dust and gas, material heated by the intense radiation environment and by the friction of material falling toward the central black hole. The infrared luminosity of the galactic centre region represents the accumulated output of an extraordinarily dense stellar population embedded in a radiation environment that keeps the surrounding gas and dust at temperatures far above what is typical in the disk. In X-rays, the galactic centre is one of the brightest regions of the sky. Multiple distinct X-ray sources contribute. The central black hole itself, which produces X-ray flares during accretion events, X-ray binaries, systems where compact objects strip material from companion stars and radiate the resulting accretion energy as X-rays, supernova remnants expanding through the dense interstellar medium of the central region, and a diffuse background of X-ray emission from hot plasma permeating the central molecular zone. In gamma rays, the most energetic and most penetrating form of electromagnetic radiation, the galactic centre is a dominant feature of the sky. The Fermi Gamma Ray Space Telescope, which has been mapping the gamma ray sky since 2008, has characterised an extended emission region centred on the galactic centre, known as the Fermi bubbles, two enormous lobes of gamma ray and radio emission extending roughly 25,000 light-years above and below the galactic plane, apparently produced by a massive energy release from the galactic centre millions of years ago. Within the Fermi bubbles and throughout the inner galaxy, gamma-ray emission from cosmic ray interactions with the dense interstellar medium adds to the radiation background. For a spacecraft approaching the galactic center, the radiation environment intensifies across all these bands as the distance closes. The intensity of electromagnetic radiation from a point source decreases with the square of the distance. Halving your distance to the galactic center quadruples the radiation flux at every wavelength. Moving from our position at 26,000 light-years to within, say, 1,000 light-years of the center, still far from the innermost regions, increases the radiation flux from the galactic center by a factor of roughly 676. This is before accounting for the additional radiation sources encountered at closer distances. The central molecular zone contains a stellar population denser than anywhere in the galactic disk, each star contributing its own radiation to the local environment. The density of X-ray binary systems in the inner galaxy is substantially higher than in the disk. Supernova remnants, the expanding shells of hot plasma left by stellar explosions, are more numerous and more recent in the inner galaxy, where the high stellar density drives a higher supernova rate. The cumulative radiation environment that a spacecraft would experience in the innermost few hundred light-years of the galaxy combines contributions from all of these sources into a broadband radiation field of extraordinary intensity. The shielding requirements to protect a human crew from this environment scale with the radiation intensity, and at the radiation levels present in the inner galaxy. The shielding mass required to maintain human survivable radiation doses inside a habitat would be so enormous that it would exceed the structural and propulsive capacity of any spacecraft conceivable with known physics. But electromagnetic radiation, as lethal as the galactic center environment would be at every wavelength, is not the most dangerous radiation threat a mission to the galactic center would face. That distinction belongs to cosmic rays, and the galactic center is one of the primary cosmic ray acceleration sites in the Milky Way. Cosmic rays are charged particles, primarily protons and heavier atomic nuclei, moving at velocities close to the speed of light. They are the highest energy particles in the universe, and they originate from a variety of astrophysical acceleration sites: supernova remnants, pulsar wind nebulae, active galactic nuclei, and, with increasing observational evidence, the galactic center. In 2019, astronomers analyzing data from the High-Energy Stereoscopic System Telescope Array in Namibia reported the detection of cosmic rays with energies up to 1 petaelectronvolt, 1,000 trillion electron volts, originating from the direction of the galactic center. 1 petaelectronvolt is approximately 100 times the energy achievable by the Large Hadron Collider at CERN, the most powerful particle accelerator humanity has ever built. The galactic center is producing particles with energies that dwarf the most energetic collisions achievable by human technology, apparently through acceleration processes associated with the central black hole and the energetic environment immediately surrounding it. These ultra-high energy cosmic rays are produced continuously, streaming outward from the galactic center region in every direction. In the galactic disk and throughout the spiral arms, the interstellar magnetic field deflects them, spreading them across directions and diluting their flux before they reach any given location. From Earth's perspective, galactic cosmic rays arrive from all directions nearly isotropically. The directional information has been scrambled by billions of years of magnetic deflection. But a spacecraft traveling toward the galactic center would be moving against the gradient into a region where the cosmic ray density and average energy increase with each light-year of approach. The flux of cosmic rays, already a primary radiation hazard for deep space missions in the outer galaxy, would intensify as the galactic center approached. The biological damage mechanism of cosmic rays is specific and devastating. A proton moving at 99.99% of light speed carries a kinetic energy measured in tens of thousands of electron volts per nucleon. When such a particle passes through biological tissue, it ionizes the atoms along its path, stripping electrons from molecules and leaving a trail of chemical damage in its wake. DNA double-strand breaks, lipid peroxidation, protein denaturation. The cellular damage from a single high-energy cosmic ray track through a cell is qualitatively different from the diffuse ionization of lower-energy radiation. The most energetic cosmic rays produce nuclear spallation. They strike atomic nuclei in the shielding or tissue and fragment them, producing showers of secondary particles that each carry significant energy and deliver their own biological damage. The heavier the shielding material, the more secondary particles are produced. Above an optimal shielding thickness, adding more shielding material increases the biological dose rather than decreasing it, because the secondary shower becomes more damaging than the attenuated primary would have been. For cosmic rays at the energies produced by the galactic center environment, there is no shielding thickness at which passive shielding becomes protective. The secondary showers generated by ultra-high energy primary cosmic rays penetrate any physically plausible shield. Active magnetic shielding, using superconducting coils to generate artificial magnetic fields that deflect charged particles, can reduce the flux of lower energy cosmic rays, but the highest energy particles carry enough momentum to curve only negligibly, even through strong magnetic fields. The radiation dose from the cosmic ray environment in the inner galaxy would exceed the biological threshold for acute radiation syndrome within hours of exposure at sufficiently close approach to the center. Chronic exposure at moderate intensities, still far higher than anything experienced in the outer galaxy, would accumulate DNA damage faster than any cellular repair mechanism can address, leading to a cascade of irradiation-induced cellular failures that would be lethal within months. The radiation environment of the galactic center is, by itself, sufficient to make human survival in its vicinity impossible, with any technology that does not violate known physics. But radiation is only the first layer of the problem. It is the layer that kills slowest. There are others that operate more immediately. At the precise geometric center of the Milky Way sits an object unlike anything in our stellar neighborhood, an object so massive that it was not confirmed to be a black hole, despite decades of indirect evidence, until the Event Horizon Telescope collaboration published the first direct image of its shadow in May 2022. Sagittarius A star, written as S-GR A star in the literature, 4 million solar masses of collapsed matter compressed into a region smaller than the diameter of the orbit of Mercury around our Sun. A gravitational singularity, a point where the density of matter becomes, in the language of the equations, infinite, and where the classical laws of physics as currently formulated stop making predictions. The event horizon of S-GR A star, the boundary within which the escape velocity exceeds the speed of light, has a radius of approximately 12 million kilometers. This is called the Schwarzschild radius. Cross it and causality itself becomes a one-way street. You can approach the singularity, but nothing, not you, not light, not any signal of any kind, can travel back outward. A human being approaching S-GR A star would encounter the gravitational influence of 4 million solar masses long before reaching the event horizon. The tidal forces of a black hole, the difference in gravitational acceleration between the near side and far side of an extended object, scale with the mass of the black hole and inversely with the cube of the distance from it. For a stellar mass black hole of a few solar masses, tidal forces become lethal at distances of only a few hundred kilometers, long before crossing the event horizon. This process has a name in the physics literature: spaghettification. The differential gravitational pull stretches any extended object along the radial direction, toward and away from the black hole, while compressing it in the perpendicular directions. A human body approaching a stellar mass black hole close enough would be stretched into a thin stream of particles long before any other environmental effect became relevant. S-GR A star, being 4 million times more massive, has proportionally weaker tidal forces at the same distance. The tidal force scales inversely with the cube of the distance, but the Schwarzschild radius scales linearly with mass, so the event horizon is much further out. At the event horizon of S-GR A star, the tidal forces are surprisingly gentle. A human body crossing the event horizon might not experience tidal forces sufficient to cause immediate structural damage, though this is somewhat academic given the other threats present. The relevant tidal forces for a spacecraft on an approach trajectory that does not aim for the event horizon, one attempting to orbit or pass through the inner few light years of the galactic center, would be dominated not by the black hole itself, but by the collective gravitational influence of the dense stellar population surrounding it. The inner parsec of the galaxy, the region within roughly 3.26 light-years of S-GR-A, contains a population of approximately 10 million stars packed into a volume that in our galactic neighborhood would contain only a handful. The stellar density in this region is roughly 10 million times higher than in the solar neighborhood. Stars in the innermost 0.1 parsecs orbit S-GR A star at velocities up to 5% of the speed of light, velocities achieved by no object in our part of the galaxy. These stars are the most directly observable evidence of Escaré star's mass. The star designated S2, the most closely observed of the so-called S-stars orbiting the galactic center, completes one orbit around Escaré in approximately 16 years, approaching within 120 astronomical units of the black hole at its closest approach, and reaching velocities of approximately 7,600 km per second, 2.5% of light speed. The orbit of S2 has been measured with sufficient precision to confirm general relativistic effects. The orbit precesses in a way predicted by Einstein's equations, but not by Newtonian gravity. For a spacecraft navigating through the inner parsec, the gravitational environment created by 10 million densely packed stars plus a 4 million solar mass black hole creates trajectory perturbations that are essentially unpredictable on any practical planning timescale. A flight path computed far in advance would be invalidated by gravitational interactions with individual stars not accounted for in the computation. The inner parsec is, from a navigational standpoint, a gravitational chaos zone, a region where the number of significant gravitational influences on any trajectory is so large that deterministic navigation becomes impossible with any finite computation. But a spacecraft crew worried about navigation at this point in the approach has already survived things that make navigation concern secondary. Throughout the disk of the Milky Way, the interstellar magnetic field maintains a strength of roughly 1 to 3 microgauss, a field so weak it is millions of times less intense than Earth's surface magnetic field, and yet strong enough, over galactic distances, to deflect cosmic rays and organize the large-scale structure of the interstellar medium. In the galactic center region, the magnetic field is not weak. Measurements of the galactic center magnetic field, derived from radiopolarization observations and Faraday rotation measurements, indicate field strengths of milligauss to tens of milligauss in the central molecular zone, roughly 1,000 to 10,000 times stronger than the typical galactic disk field. In the immediate vicinity of Esca-AEN, theoretical models and observational constraints suggest magnetic field strengths approaching milligauss at distances of parsecs, increasing toward Gauss-level fields closer to the event horizon. A magnetic field of milligauss strength, roughly 100 to 1,000 times weaker than Earth's surface field, is not immediately dangerous to human biology through direct field interaction. The human body is largely non-magnetic, and static magnetic fields at these strengths, while detectable by sensitive medical imaging equipment, do not directly damage biological tissue. MRI machines routinely expose human patients to fields of 1 to 3 Tesla, millions of times stronger than the galactic center field, without biological harm from the field itself. The danger of the galactic center magnetic field is not direct biological effect, it is what the field does to the radiation environment. Charged particles, cosmic rays, energetic electrons, ionized gas spiral along magnetic field lines, accelerated and deflected by the field geometry. In a strong magnetic field, the pitch angle of a charged particle's spiral motion is determined by the ratio of its velocity component along the field to its velocity component perpendicular to it. Strong fields confine charged particles to tight spirals, concentrating their density along field lines and creating highly anisotropic radiation environments, where the direction you face, relative to the field geometry, determines how much radiation you're exposed to. In the galactic center magnetic field, this concentration effect creates filamentary structures of intense radio emission. The non-thermal radiofilaments, first detected in the 1980s, that appear as bright linear structures in radio images of the inner galaxy. These filaments represent regions where relativistic electrons are concentrated by the magnetic field, radiating synchrotron emission along their length. Their existence implies that the magnetic field of the galactic center is not merely a background feature of the environment, but an active organizer of the energetic particle population, herding relativistic particles into structures that would deliver locally intense radiation doses to anything passing through them. The galactic center magnetic field also drives plasma heating through magnetic reconnection, the process by which oppositely directed magnetic field lines annihilate each other, releasing their stored energy as heat and particle acceleration. In the solar corona, magnetic reconnection drives solar flares. In the galactic center, where the magnetic field is stronger and the plasma density higher, reconnection events release energies that dwarf anything in our solar neighborhood, contributing to the overall radiation budget of the inner galaxy and adding episodic intense radiation events to the continuous background. A spacecraft in the galactic center environment would need to navigate not only the average radiation level, but the structured radiation landscape created by the magnetic field, avoiding filamentary concentrations of relativistic electrons, predicting reconnection events, managing the directional dependence of the radiation environment as the field geometry changes with position. No spacecraft we can currently build has the sensor suite, computing capacity, or maneuverability to navigate this environment safely. And the crew inside it, shielded as best as available technology permits, would be receiving radiation doses that make the question of navigation somewhat academic. The galactic center is not a dead zone of old stars quietly orbiting a central black hole. It is an active stellar nursery, one of the most vigorous sites of star formation in the Milky Way, and the consequence of that activity for anything biological in the vicinity is catastrophic. Star formation requires dense gas clouds, regions where gravity can overcome the thermal pressure that otherwise prevents collapse. The central molecular zone, the inner 1,000 light-years of the galaxy, contains approximately 50 million solar masses of molecular gas, a significant fraction of the Milky Way's total molecular gas budget, concentrated into a tiny fraction of its volume. This gas is denser, warmer, and more turbulent than the molecular gas in the disk, driven to these extreme states by the gravitational potential of the galactic center, the radiation pressure of the intense radiation environment, and the mechanical energy injected by stellar winds and supernova explosions. Despite the extreme turbulence, which on the face of it should suppress star formation by dispersing gas clouds before they can collapse, the galactic center manages to form stars at a significant rate. The Arches cluster and the quintuplet cluster, two of the most massive and densest young star clusters known in the Milky Way, both reside within about 100 light-years of star A. Each contains tens of thousands of stars, with a significant population of massive stars, O and B supergiants, burning at luminosities hundreds of thousands of times that of our Sun. Massive stars live fast and die violently. A star of 60 solar masses exhausts its hydrogen fuel in roughly 3 million years, less than 1% of our Sun's expected 10 billion-year main sequence lifetime, and then explodes as a supernova. The explosion releases approximately 10 to the 44th joules of energy, the equivalent of our Sun's entire 10 billion-year energy output compressed into a few seconds. The explosion accelerates the stellar core to implosion and launches the star's outer layers outward as an expanding shell of hot plasma, travelling at velocities of 10,000 kilometers per second or more. In the galactic disk, supernovae are relatively rare, one every 50 to 100 years in the Milky Way as a whole, distributed across a disk 100,000 light-years in diameter. The average distance from any point in the disk to the nearest recent supernova remnant is hundreds of light-years. A supernova close enough to deliver a lethal radiation dose to Earth's surface would need to occur within roughly 30 light-years, an event that happens perhaps once every few 100 million years. In the central molecular zone, the supernova rate is orders of magnitude higher per unit volume. The dense stellar population, with its overrepresentation of massive short-lived stars, produces supernovae far more frequently and in a far smaller volume than the disk. The SGRAE supernova remnant, a shell of hot plasma centered near the galactic center, appears to be the product of multiple supernova events within the past few 100,000 years, creating a hot plasma cavity that encompasses the immediate environment of the central black hole. A spacecraft attempting to navigate the inner galactic center region faces a probabilistic hazard from supernovae that is qualitatively different from anything in the outer galaxy, not a once-in-a-geological-epoch event, a statistical certainty over any mission timescale longer than years that a nearby stellar explosion will occur, releasing radiation pulses that, at galactic center distances, would overwhelm any conceivable shielding. The prompt radiation from a nearby supernova, the burst of X-rays and gamma rays emitted during the first seconds of the explosion, travels at light speed and provides no warning. The relativistic particle component follows closely behind. A spacecraft within a few light-years of a supernova explosion would receive, in minutes to hours, a radiation dose measured in thousands of sieverts, hundreds of times the lethal threshold for acute radiation syndrome. There is no shelter from a nearby supernova. There is no shielding that absorbs the prompt gamma-ray pulse from a stellar explosion at close range. The event horizon of warning time is defined by the speed of light, and the prompt radiation arrives at light speed, indistinguishable in its advance from the ordinary background until it arrives. In the galactic center environment, where the supernova rate is high and the stellar population guaranteeing future explosions is dense and young, this is not a remote statistical risk. It is a scheduled certainty whose exact timing is unknown. In 2010, astronomers analyzing data from NASA's Fermi Gamma Ray Space Telescope discovered something extraordinary about the structure of our galaxy. Extending above and below the galactic plane, centered on the galactic center, are two enormous lobes of gamma-ray emission, each spanning approximately 25,000 light-years, together forming a structure roughly 50,000 light-years in total extent. The lobes are nearly perfectly symmetric, suggesting they were produced by a single energetic event at the galactic center, rather than by the accumulated activity of many sources. They have been called the Fermi bubbles. The energy required to inflate the Fermi bubbles to their observed size, against the pressure of the surrounding interstellar medium, is estimated at approximately 10 to the 55th joules. This is roughly the equivalent of 10 million supernova explosions, or the entire energy output of our Sun sustained for 10 billion years, concentrated into a period of perhaps a few million years. The event that produced them was almost certainly associated with a period of dramatically elevated accretion onto Esgara star, a phase when the central black hole was consuming in falling matter at a rate orders of magnitude higher than today, converting the gravitational potential energy of the accreting material into jets or winds of energetic particles and radiation that inflated the lobes. The Fermi bubbles are not currently dangerous to Earth. They are expanding outward from the galactic center and are separated from our solar system by tens of thousands of light-years of space. Their edges pass nowhere near our galactic neighborhood. But they testify to something important about the nature of the galactic center, its history of episodic, catastrophically energetic events that transform the radiation environment of the entire inner galaxy. The most recent major activity of Esgara star, the event that inflated the Fermi bubbles, occurred perhaps 3 to 4 million years ago. In cosmological terms, this is recent. The ancestors of our genus, Homo, were walking upright on the African savanna when the galactic center was erupting with an energy release that would have been visible from Earth as a brilliant point of light at the heart of the Milky Way, potentially rivaling the full moon in brightness. Since then, Esgara star has been relatively quiet. Its current accretion rate is low. The black hole is starved of infalling material compared to its previous state, and its X-ray luminosity is many orders of magnitude below what it must have been during the Fermi bubble inflation event. But it is not inactive. X-ray flares from Esgara A are detected multiple times per day, brief intensifications of X-ray emission, lasting from minutes to hours, apparently produced when small clumps of gas fall onto the black hole and release energy through the accretion process. These daily flares are currently modest. At Earth's distance, they are scientifically interesting but not biologically consequential. At close range, within a few light years of Esgara A, they would represent significant radiation events. At even closer range, within a fraction of a light year, they would be lethal. And the history of the Fermi bubble suggests that the current quiet period is not permanent. Esgara A has been in an active state before, it will be in an active state again. The triggering mechanism, the infall of a gas cloud, the disruption and accretion of a star, the arrival of a dense cloud of infalling material, is unpredictable on timescales of less than millions of years. A mission to the galactic center would need to contend not only with the present radiation environment, but with the statistical probability that the central black hole could enter a more active accretion phase on any timescale from years to centuries. An awakening of Esgara star, even a modest one by the standards of active galactic nuclei, would transform the radiation environment of the inner parsecs from merely lethal to instantaneously lethal. There is no escape route from the center of the galaxy that operates faster than the speed at which its radiation travels. Between our location in the outer galaxy and the death zone of the innermost parsecs lies a region that would kill any mission long before the black hole or the supernovae had a chance to. The central molecular zone, spanning the inner 1,000 light-years of the galaxy, The CMZ is a ring of dense molecular gas and dust orbiting the galactic center at velocities of roughly 100 to 200 kilometers per second. It contains some of the most massive and dense gas clouds known in the Milky Way, objects like SGR-B2, a molecular cloud complex with a mass of roughly 3 million solar masses compressed into a region a few hundred light-years across, making it one of the most massive molecular structures in the galaxy. These clouds are not static. They are turbulent, churned by the gravitational influence of the galactic center, by the winds from massive stars embedded within them, by supernova explosions in the dense stellar population nearby, and by tidal forces from the combined gravitational potential of the inner galaxy. Gas velocities within individual clouds range from tens to hundreds of kilometers per second, velocities at which a collision with even a small gas clump would be energetically significant for a spacecraft. The dust content of these clouds is also relevant. Interstellar dust particles, solid grains of silicates and carbonaceous material, ranging from nanometers to micrometers in size, are embedded throughout the molecular gas. At the densities present in the central molecular zone, dust opacity becomes significant. The clouds are genuinely opaque to visible light, which is why the galactic center itself is invisible at optical wavelengths and can only be observed at radio, infrared, and X-ray wavelengths. A spacecraft traveling through the CMZ would be traveling through clouds dense enough to scatter and absorb optical wavelengths, creating navigation challenges that further compound the mechanical hazards of the gas environment. The chemical environment of the CMZ is also extraordinary. Complex organic molecules, amino acids, sugars, aromatic hydrocarbons, are abundant in galactic molecular clouds throughout the disk. But the CMZ has an additional feature. High cosmic ray ionization rates from the intense local cosmic ray flux catalyze chemical reactions in the cold, dense gas that produce complex molecular species not found in quieter molecular cloud environments. The chemistry of the CMZ is driven partly by energetic particle bombardment, as much as by photochemistry, creating a molecular environment unlike anything in the outer disk. None of this is directly lethal in the way that radiation is lethal, but it creates an environmental context that makes the passage through the CMZ hazardous in ways that compound the radiation environment. The gas and dust moderate some radiation while adding mechanical collision hazards, and the navigational opacity of the clouds makes trajectory planning unreliable. A mission penetrating the CMZ from the outside inward is a mission entering a region where visibility in the conventional sense is gone, where the gas environment creates collision risks at the microscale, and where the radiation environment is already elevated far above survivable levels without extraordinary shielding. There is a dimension of a mission to the galactic center that has nothing to do with radiation or gravity or stellar explosions. It has to do with time, distance, and communication. And it is, in some ways, the most existentially absolute of all the challenges. The galactic center is 26,000 light-years away. A signal sent from the galactic center travels at the speed of light and takes 26,000 years to arrive at Earth. Earth's response takes another 26,000 years. A complete round-trip communication takes 52,000 years. The entire recorded history of human civilization spans approximately 5,000 years. A message sent from the galactic center would arrive at Earth after a delay more than 5 times longer than the entire history of every human culture that has ever existed. The civilization that launched a mission to the galactic center and the civilization that received its first communication would be separated by a temporal gulf longer than the gap between us and the builders of Stonehenge, multiplied by 10. The crew of a galactic center mission would be, in the most complete possible sense, alone. Not alone in the way deep space astronauts are alone, receiving delayed but regular communication from Earth, maintained in contact with a recognizable and familiar civilization. Alone in the way that the word stops conveying anything meaningful and becomes simply a fact of physics. The crew would be human beings in a metal ship 26,000 light-years from another human being, in an environment designed to kill them, with a communication delay measured in tens of thousands of years. Any return journey, at any velocity achievable with known physics, would take longer than human civilization has existed. The crew that departed would not return. Their children would not return. Their descendants hundreds of generations removed would not return within any time frame that connects the mission to the civilization that launched it. A mission to the galactic center, under known physics, is a one-way trip. Not in the romantic sense of early explorers who knew they might not make it back. In the absolute physical sense of a journey whose round-trip time at maximum achievable velocity exceeds the expected lifespan of any civilization that might be waiting. This does not make the mission impossible in principle. It makes it a different category of endeavour from anything in the history of human exploration. A commitment not of a crew, but of a lineage. Not of a decade, but of a geological era. Not of a civilization, but of whatever that civilization chooses to send forward into the dark as its representative. The first humans to enter the galactic center environment, if they ever do, will be sending messages back that no one alive when they departed will be alive to receive. They will be speaking across time as much as across space. They will be, in the most literal possible sense, beyond reach, beyond help, beyond rescue, beyond any form of connection with the species that produced them, except the one-way flow of information travelling at the speed of light across 26,000 years of empty space. And they will be doing this inside a radiation environment that is trying to kill them. As a spacecraft approaches within fractions of a light-year of Escura star, the gravitational dynamics transition from the merely chaotic to the genuinely exotic. In the innermost region around a supermassive black hole, the density of stars is so high and their orbital velocities so extreme that stellar collisions, events of negligible probability anywhere else in the galaxy, become a meaningful statistical occurrence on astronomical timescales. Stars in the innermost 0.01 parsecs of the galactic center have orbital velocities of several percent of the speed of light and orbital periods of only years. The mean time between close stellar encounters in this region is short enough that stellar surface grazing encounters and even collisions have occurred within the past million years. The same gravitational environment that drives these stellar interactions creates a class of event called tidal disruption events, moments when a star passes close enough to the central black hole that the tidal forces exceed the star's own self-gravity and tear it apart. The disrupted stellar material forms an elongated stream, roughly half of which falls back onto the black hole along highly eccentric trajectories, and half of which is ejected at high velocity into the surrounding environment. The fallback accretion produces a bright flare of electromagnetic radiation across optical, UV, and X-ray wavelengths that can be more luminous than the entire galaxy for weeks to months. Tidal disruption events at Escura star are estimated to occur roughly once every 10,000 to 100,000 years. Infrequent by human standards, but occurring at a rate that means several have happened since anatomically modern humans appeared. Each one temporarily transforms Escura A from its current quiescent state into a luminous accretion source, not as powerful as a full quasar, but bright enough to illuminate the surrounding molecular gas with ionizing radiation, and to drive powerful winds of material into the surrounding parsecs. A spacecraft present in the galactic center during a tidal disruption event would have no warning. The triggering stellar encounter happens at speeds and scales that cannot be predicted far in advance, and no survival option. The radiation pulse from a tidal disruption event at close range would be instantly lethal across any shielding thickness achievable with known materials. The probability of a spacecraft present in the inner parsecs for an extended period, coinciding with a tidal disruption event, is not zero. Over years of mission time in this environment, it rises from negligible toward significant. Over decades, it becomes a near certainty. We have now travelled through the full catalogue of what makes the galactic centre a death trap. The radiation, electromagnetic and cosmic ray, from the densest concentration of energetic astrophysical phenomena in the Milky Way. The gravitational chaos of 4 million solar masses of black holes surrounded by 10 million densely packed stars. The magnetic field thousands of times stronger than our galactic neighbourhood, herding charged particles into filamentary structures of intense local radiation. The stellar population producing supernovae at rates that make a nearby explosion a statistical certainty on any multi-year mission timescale. The dense molecular gas of the central molecular zone creating optical opacity, chemical complexity and mechanical hazards for any spacecraft traversing it. The episodic violence of tidal disruption events that temporarily convert Escura star from a quiet black hole to a radiation source of extraordinary luminosity. the absolute communication isolation of a position 26,000 light-years from Earth, beyond any meaningful connection to the civilization that launched the mission. Each of these challenges is individually formidable. The compound threat they represent, the way each intensifies the others, the way the radiation makes the psychological isolation more severe, the way the navigation uncertainty combines with the communication delay to create a mission with no external support and no reliable path planning, creates a survival environment qualitatively different from anything else in the galaxy accessible within our light cone. But there is something else to say about this catalogue, something that the list of threats, taken purely as a list of obstacles, does not communicate. The same conditions that make the galactic centre deadly are the conditions that made our location possible. The galactic habitable zone is not an accident of stellar geography. It is a consequence of physics. The inner galaxy is violent because it is dense. Dense in stars, dense in gas, dense in gravitational and electromagnetic energy. That density drives star formation at high rates, which means supernovae at high rates, which means radiation at lethal intensities, which means that anything biological in the inner galaxy has been bombarded continuously by the very processes that also make the inner galaxy rich in heavy elements. The outer galaxy is quiet, stars are spread thin, supernovae are rare, the radiation environment is manageable, not harmless, but compatible with the existence of magnetic shields like Earth's, which can deflect enough of the cosmic ray flux to allow life to persist on a planet's surface for billions of years. The galactic habitable zone, the region where we exist, is defined by the boundary between too much and too little. Too close to the centre and the violence of the active stellar population, the intense radiation environment, the gravitational chaos, and the episodic energetic outbursts of the central black hole make biological complexity impossible. Too far from the centre and the heavy element abundance drops too low. The raw materials for rocky planets, for complex chemistry, for the biochemical machinery of life, become scarce. We exist precisely in the narrow ring where both constraints are satisfied simultaneously, where the radiation environment is intense enough to have driven the heavy element enrichment that gave us the atoms we're made of, but diluted enough by distance that the magnetic field of a rocky planet can protect a biosphere for geological timescales. Where the supernova rate is high enough to have seeded the interstellar medium with the products of stellar nucleosynthesis, but low enough that nearby explosions are geological rarities rather than annual threats. The galactic centre is a death trap not despite being the centre of the galaxy but because of it. The same processes that make it lethal, the high mass concentration, the intense stellar activity, the powerful radiation fields, the energetic black hole, are the processes that drove the chemical enrichment of the galaxy that made our existence possible. The galactic centre cooked the elements. The galactic arm delivered them, safely diluted by distance, to the quiet backwater where they assembled into us. We are, in a precise physical sense, the beneficiaries of the galactic centre's violence. The carbon in your cells was forged in the cores of massive stars. The iron in your blood was scattered by supernovae. The calcium in your bones was produced in neutron star mergers. All of this was driven by the same astrophysical violence that makes the galactic centre impossible to visit. The death trap made us, and then put us far enough away to survive it. There is a philosophical dimension to the galactic centre's hostility that extends beyond the catalogue of physical threats. Every environment in the universe that is energetically rich, every place where astrophysical processes operate at high intensity, is also an environment hostile to the specific kind of ordered complexity that constitutes life. This is not a coincidence. It is a consequence of thermodynamics. Life is a local, temporary, sustained decrease in entropy, a structure that maintains itself against the universal tendency toward disorder by consuming energy and exporting entropy to its surroundings. The delicate molecular machinery of biology requires a narrow operating range of temperature, radiation level, and chemical composition. Too much energy input disrupts the molecular bonds that hold the machinery together. Too little energy input and the machinery cannot sustain itself against thermal degradation. The galactic centre represents too much, far too much. Energy densities so extreme that the molecular organisation required for life is continuously overwhelmed, not just occasionally disrupted, but systematically prevented from assembling in the first place. The radiation environment alone, even ignoring gravitational, magnetic, and explosive threats, would shatter the chemical bonds of complex organic molecules faster than any plausible chemistry could form them. This is a statement about the limits of life as we know it. It is possible, not proven, but not prohibited by physics, that life could take forms radically different from carbon-based biochemistry, forms that operate under energy densities and radiation environments that would destroy anything familiar to us. But the physics of chemical bond energies is not negotiable. Bonds that store the information of a genetic code, bonds that maintain the folded structure of a functional protein, bonds that sustain the electrochemical gradients of a living cell, these are quantum mechanical structures with characteristic energy scales in the electron-volt range. The radiation environment of the galactic center delivers energies millions to billions of times higher than the binding energies of the molecules of life. No arrangement of familiar chemistry survives in that environment. The galactic center is not hostile to life the way that a desert or a deep ocean trench is hostile to life. Harshly, but not prohibitively, with some forms of life finding ways to persist at the extremes. It is hostile to life the way that the core of a stellar explosion is hostile to life. Fundamentally, structurally, at the level of whether the chemistry that supports metabolism can exist. Understanding this teaches something important about the relationship between energy and complexity in the universe. The most energetically active regions are the least hospitable to the most complex structures. The quietest regions, the galactic suburbs, the stable arms, the long-lived stars with habitable zones, are the places where complexity has time and space to build. The universe produces its most elaborate structures in its quietest corners, and the galactic center, roaring with radiation, churning with gravitational violence, periodically convulsed by the accretion events of its central black hole, is the loudest corner of all. On a clear night, from a dark location in the southern hemisphere, or from the right latitude in the northern, you can look toward the constellation Sagittarius and know that the galactic center is there. You cannot see it. The central molecular zone blocks the optical light from the galactic center behind roughly 30 magnitudes of visual extinction, a factor of 1 trillion in brightness reduction. The photons of visible light from the stars crowding the innermost parsecs around SGA have been absorbed by the dust of the CMZ before they could travel more than a few hundred light-years from their sources. The galactic center is optically invisible from Earth, hidden behind the galaxy's own material, but the radio waves pass through the dust. The infrared passes through, the X-rays, the gamma rays, they reach Earth's vicinity, where satellite observatories above the absorbing atmosphere collect and record them. The picture of the galactic center, built from these multi-wavelength observations, is the most complete portrait of an astrophysical environment humanity has assembled. It shows us a place of extraordinary beauty and extraordinary violence. Dense stellar clusters glowing in the infrared, X-ray binary systems flaring in the high-energy sky, the precise location of SGA pinned by decades of stellar orbit tracking, the shadow of the black hole's event horizon itself now directly imaged, and it shows us something that is not comforting but is important, that the universe at its most energetically active is not a place for us, that the conditions required for complex chemistry, for biological organization, for the sustained low-entropy structures that constitute living things are conditions of relative quietude, low radiation, modest gravitational gradients, stable energy sources, long timescales of undisturbed chemical evolution. The galactic center is a death trap, not for any malicious reason, not because the universe has arranged itself to exclude us, but because it is what it is. 4 million solar masses of collapsed matter surrounded by 10 million densely packed stars in a radiation environment of extraordinary intensity, and we are what we are, arrangements of carbon and water and electrochemistry that evolved in a quiet backwater, 26,000 light-years from all of that. The death trap made us possible. The distance from the death trap made us real. Look towards Sagittarius tonight. Know that behind the dust and the stars, something enormous and violent sits at the center of everything you have ever lived inside. Something that has been there for billions of years, shaping the galaxy, driving the chemical enrichment that produced every atom in your body, periodically erupting with energies that briefly rival the output of entire galaxies. It is 26,000 light-years away. It is the reason you are here, and it is the reason you cannot go there. Some distances are not barriers, they are gifts. The distance between us and the galactic centre is the most important gift in the history of life on Earth. And tonight, looking up at the Milky Way arching overhead, knowing what is at its centre, knowing what that centre does to everything that comes near it, knowing that your existence depends not just on the presence of a suitable star and a rocky planet and liquid water, but on being far enough from the most violent place in the galaxy to survive it. That distance should feel different, not empty, protective. The dark between you and the centre is not nothing. It is exactly the right amount of space.